Welcome in Core. Recent research suggests that the movement of our solar system through the galaxy could impact Earth's climate. Millions of years ago, passing through a dense interstellar cloud might have disrupted the sun's protective heliosphere, allowing more cosmic material to reach Earth. This could have caused climate cooling events like ice ages and even influenced human evolution. In this video, we explore how galactic movement may have shaped Earth's climate and what it means for the future. The heliosphere and its role. To understand how interstellar clouds might affect Earth's climate, we need to first explore the heliosphere, the protective bubble formed by the sun's solar wind. The solar wind, a continuous flow of charged particles from the sun, extends far beyond Pluto and shields the solar system from harmful cosmic radiation and interstellar material, ISM, the gas and dust that exists between stars. The heliosphere is essential for protecting Earth. Without it, the planet would be exposed to higher levels of radiation, which could damage our atmosphere and disrupt life. This bubble acts as a shield, keeping dangerous cosmic rays at bay. However, the heliosphere isn't static. It's influenced by the solar system's motion through the galaxy. As the sun orbits the center of the Milky Way, it moves up and down above and below the galactic plane, periodically entering regions of space with varying densities. Currently, it is in the local bubble, a low-density region with around 0.001 particles per cubic centimeter. This environment offers protection for Earth. However, as the solar system moves, it will eventually leave this relatively calm region and enter denser interstellar clouds. These dense molecular clouds can have significantly higher particle densities, and their presence can compress the heliosphere. When it encounters such clouds, the heliosphere's protective effect weakens and more interstellar material enters it, potentially affecting Earth's atmosphere. The impact of dense interstellar clouds. A recent study suggests that the solar system passed through a dense interstellar cloud around 2 million years ago, which may have influenced Earth's climate. These molecular clouds, denser than the surrounding space, contain more than 1,000 particles per cm compared to the sparse conditions in the local bubble. When it moves into such a cloud, the pressure can compress the heliosphere. As a result, the protective solar wind is reduced, exposing Earth to higher levels of cosmic radiation, hydrogen, and dust. This increased exposure could have had several effects on Earth. One of the most significant impacts could have been on the ozone layer. The ozone layer acts as Earth's shield against harmful ultraviolet radiation. But if it were weakened by increased cosmic radiation, more UV rays would reach the surface. This would likely have caused global cooling and could have contributed to the onset of ice ages by altering cloud formation, atmospheric chemistry, and radiation absorption. These cosmic events could have influenced the planet's overall temperature. Such cooling events may have been critical in shaping Earth's climate history. The exposure to a denser region of space would have had far-reaching effects on atmospheric processes, leading to significant changes in global temperatures. These fluctuations in temperature could have led to the development of ice ages, periods of significant global cooling that dramatically altered the environment. The study also suggests that these galactic encounters may not be a one-time event. While it is currently in the calm local bubble, it will eventually encounter denser regions again. Such encounters could compress the heliosphere once more, possibly affecting Earth's climate in the future. Evidence from geological records and implications for climate. The idea that galactic events could influence Earth's climate is supported by geological evidence. Researchers have found elevated levels of isotopes like iron-60 Fe and plutonium-244-24 Pu in ice cores, ocean sediments, and even lunar samples. These isotopes, which are not naturally produced on Earth, are believed to originate from distant supernova and neutron star mergers. When these events occur, they release large amounts of isotopes that become trapped in interstellar dust, which can then enter planetary systems. The presence of these isotopes in Earth's geological record strongly supports the idea that the solar system passed through a dense molecular cloud. The levels of iron-60 found in the record suggest that these particles were deposited during an encounter with a molecular cloud rather than a nearby supernova. While a nearby supernova could have compressed the heliosphere to dangerous levels, the isotopic evidence suggests that it passed through a cloud that was dense enough to expose Earth to higher levels of cosmic radiation without the extreme effect of a close supernova. This isotopic evidence not only provides insight into the history of cosmic events, but also strengthens a hypothesis that interstellar clouds may have had a role in shaping Earth's climate by impacting atmospheric processes and potentially triggering cooling events. These encounters could have contributed to the onset of ice ages or other climatic shifts. The evidence from ice cores and lunar samples offers a window into Earth's interaction with the wider galaxy, revealing the long-term influences of galactic forces on our planet's environment. Isotopic deposits align with climatic shifts, suggesting cosmic events, not just terrestrial factors, drove global cooling. This theory provides new insights into Earth's climate drivers and how cosmic events may have influenced life and human evolution. Outro, this study reveals that the solar system's movement through the galaxy could impact Earth's climate with encounters with interstellar clouds possibly triggering global cooling and ice ages, challenging the belief that climate change is solely driven by terrestrial factors. This research suggests cosmic forces play a significant role. As the sun continues its journey, similar events could occur again. Stay tuned as more research uncovers how these cosmic interactions shape life on Earth. Thanks for watching Dark Core.